All right, hello everyone. Today, this lesson, we're going to be talking about nuclear decay, which is the opposite for nuclear reactions. For this lesson, we're going to be able to create models for radioactive decay for three different types of decay models, and also to explain the half-lives. So last time we talked about strong nuclear forces. Now we're going to talk about weak nuclear forces. So these are forces that govern how particles decay. So because atoms decay over time, which reduces its radioactivity. So like this image here, we see a large atom that is emitting some particles. This is it decaying. So for this, we're going to talk about half-life. Actually, not the game. We're going to talk about nuclear half-lives. Half-life is the amount of time it takes for an element or molecule to decay half of its atoms and also reduce its radioactivity by half. So if you decay half of its atoms or molecules, then that element will reduce to half its mass. The example I have here is cobalt-60, where we see a decay. It starts as 10 grams, and you can see that over time, it starts to reduce by half. So right here at 100%, at 50% have 5 grams, 25%, 2.5, 12.5%, 1.25, etc. And the bottom is the amount of half-lives. And it says that each half-life for cobalt-60 is around 5.27 years. So this number one is after 5.27 years. This is 10.54, and etc. Keeps on adding 5.27 years each time. So half-life can it can be varied based on the material that we're talking about. Some can be very short. So like francium-223 has a half-life of only 22 minutes. While on the other hand, uranium-238 has a half-life of literally 4.5 billion years. So literally can be a span of minutes or billions of years. So it can tell you can probably solve problems using half-lives. So this is give you an example problem. Let's say we have an element X that has a half-life of 25 years. We have 400 grams of element X before it started decaying, but how long would it take for it to decay to have 25 grams? So let me show you how I'll do this problem. So we said that the half-life was 25 years, right? And then we also said that it originally has 400 grams. But we want to go to 25 grams. So how long would that take? So what we had to do is just start at 400 grams and then reduce it by half until we get 25. So 400 goes to 200. Then it goes to 100 divided by 2. And then it goes to 50. Then it goes to 25. All right. So to go to 400 and to 200, that's one half-life. 200 to 100, that's a second half-life. 100 to 50, a third half-life. And 50 to 25, 4 half-lives. So we had the element X when 4 half-lives total. So if our half-life is it's 25 years, that means total time would be 25 times 4, or 25 years for 4 half-lives. So that's 100 years. So it would take 100 years for this element X to go down to 25 grams if we started from 400. All right. as you can probably tell, we can do another problem, another similar problem. So carbon-14 has a half-life of 5,730 years. We originally had 64 grams of carbon-14, which its mass be in 17,190 years. So in this case, we have how much time we took, but we want to know the final mass. So it's basically the opposite of the other problem. So let's just write down what we know. Our half-life is 5,730 years. That's ugly. And we spent total time. We spent 17,190. So how much half-lives are that? Easy way to do this is just take our number and divide it by how many half-lives? That's just 3 years. Or not 3 years, sorry, 3 half-lives. Okay. Oops, sorry about that. And then we said we originally have 64 grams of carbon. So we're going to have 64 grams and then change it to 3 half-lives. So 1 half-life will go to 32. Another half-life will go to 16. And the last half-life will go to 8 grams. So we went to 64 and then divided by 2 3 times. So 64 half, 32, 32 half, 16, 16 half, 8. So total we have we'll have 8 grams of carbon-14. I'll give you some practice problems for half-lives. All right. So why do we care about half-lives? Well, it's important for us to know how long a radioactive element will stay radioactive, because we know uranium is used for power plants, but based on uranium-238, where it has a half-life of billions of years, it'll take a long time for the reactivity to go down to safe levels. So this is why, even though nuclear power doesn't provide environmental impacts, it's still dangerous, because that radioactive elements are still dangerous to humankind and also just the environment in all different ways. So while we won't produce fossil fuels, it's still dangerous if we don't control the radioactive elements. So that's why nuclear power we don't consider it as a renewable source, because it takes so long for the radioactive elements to be environmentally and safe for humans. Right. This lesson split up into 2 videos. The next video we're going to talk about the 3 different types of decay. All right, we'll see you next video.